Hey guys, this week we are going to talk about Chapter 4, Section 2 and Chapter 4, Section 3 in the textbook. The first thing we're going to talk about, last week we talked about global maxes and mins. This time we're going to talk about, local maxes and mins, and this week we're going to talk about what is a global maximum and a global minimum. We're going to talk briefly about the extreme value theorem. And in 4.3, we're going to be dealing with a lot of word problems. And just as a preface, 4.3 in particular, when we get to that, is a little bit challenging because basically we're trying to set up calculus problems from word problems. And so I just want to preface that, by saying that. And, I remember taking calculus in high school or college or whenever. And I remember getting to this and it being, a little bit of a stumbling block for me. So I just want to let you guys know that, when we get to 4.3, if it is a little bit challenging, that's okay. It's going to get better. This is just a particularly, it's a different topic because, as I said, we're going to be doing a lot of word problems, and that requires you to sort of draw pictures, and things like that. So, all right, without further ado, let's go ahead and get started. So last week we talked about local maxes and mins, and what those were, local maxes are points on the graph that are higher than the points near them, and local mins are the points on the graph that are lower than those nearby. So we have some examples here. In red, we have the local maxes. We can see that all of these 3 points are higher than the ones close to them. Right? The y value is larger, in other words. And then the opposite is true for the local min. The nearby points have a higher y value than the local min. So that's just kind of a reminder of, local max and local min. Okay. So the next thing we're going to talk about is global maximums and minimums. Now, sometimes in other textbooks you might see the word absolute maximum and minimum, but it means the same thing as global max and min. And basically, that the global maximum is the highest point on the entire graph, like the highest y value you can find. Now, obviously, if we have some weird kind of graph that has like a vertical asymptote or something, and the curve, that's a bad example. Maybe something like, something like a parabola maybe. And I asked, what's the global maximum of this? Well, there isn't any because the y values get as big as we want, right? If we're talking about any x value to, if we plug in any x value into the function x squared, then we can get any y value we want. So in that case, there would be no global max. Now, the lowest point on the entire graph is called the global minimum. And so, and another way of writing this is in the following way. A function f has a global max at a point p if f of p is greater than or equal to all values of f. Basically, what this is saying is that the y value is bigger than all other y values at x equals p. And the opposite is true for global minimum. So there's a global minimum at an x value p if f of p, the y value at p, is less than or equal to all values of f, so all other y values. And we can see on this picture that the first guy is a global max. We can see that. It's the highest point on the entire graph. Compare all y values, right? And it's slightly higher than this one. I mean, just barely, but it's still higher. And this is also, it doesn't say this on the picture, but this is also a local max. It's an endpoint, and that's okay. But it is higher, like the y values are higher than the points nearby. All right, so that's also a local max. This guy is a local min, but it's not a global min because it is not the lowest value. This guy is going to be the lowest value. It's just slightly lower than this guy right here. So that's just a local min because relative to the points around it, it's the smallest y value. It has the smallest y value. Local max. Again, local min, we have this dip, local max, this hump right here. And then we have the global and local min right here. This guy is a local max. And I also want to talk about this endpoint right here. So this is technically a local min because it is, the y value here is lower than the points very close to it. Okay, so this endpoint is also technically a local min. Okay. All right, so I'm going to briefly talk about the extreme value theorem. Basically, it just says if we have a function, if we have a curve on some, restricted x values, x interval, then the function has a global max and a global min on that interval. We talked about, and this is important, this interval business, this closed interval business, because what I just mentioned, I just said this guy does not have a global max. What do I really mean by that? Well, I mean on the domain, all real numbers. In other words, x can be anything. If x can be anything, there's no global max because if I plug in anything for x, I can get anything out for y. So there's no highest y value. It just keeps going up and up. However, I could restrict the domain. I could say, and that's where this comes into play. I could say, what is the global max of y equals x squared on the interval? So a in this case is 0, and b in this case is 1, between 0 and 1. Well, that's good, okay? So that cuts off some stuff. It's going to cut off all this stuff, and it's going to cut off all of this stuff, and so now we're just kind of left with this thing, and certainly there is a highest and lowest value here, okay? That's what the extreme value theorem says. If we have a closed interval, such as we have here, and a curve, we can always find a global max and a global min. And, you guys can look at these 3 examples, to look at some different curves where we have different, and notice they say absolute. That's the same thing as global. Global and absolute mean the same thing. So, okay, that is what I wanted to say there. So here is how we go about finding global maxes and mins in calculus. Well, first of all, if we have a closed interval, we need to find the critical points, and remember that we do that by taking the first derivative and setting it equal to 0. That's how we find the critical points from last time. Once we have that, we punch that into the original function. So evaluate the original function at those x values. And we're not only going to do that, but we're also going to plug in the endpoints of the interval. So for example, in the previous slide, I had this y equals x squared business. And I wanted to know I wanted to know what is the global max between 0 and 1. And so the first thing we do is we find the critical points. So the critical points come by taking the derivative and setting it equal to 0. Okay? So if we set this equal to 0, we get 2x equals 0. Therefore, my only critical number, or my critical point, is that x equals 0. Now, when they say evaluate the function at the critical points, we're plugging in 0 into the original function, not the derivative. Okay? So what do we get? We get y equals 0 squared, which equals 0. So we just evaluated the original function at the critical point. The second step is to evaluate the function at the endpoints. So these are the endpoints. So we're going to do, well, we already did 0. 0 just happened to be a critical number and an endpoint. If I evaluate my function at 1, I get 1. And the local, or the global max, is going to be the highest number that you get from this process. And that's this number. So 1 is the global max here. In a similar way, the smallest number that you get from this process is the global min. So 0 is the global min here. All right, and we're going to do some examples, so, okay. All right, so find the global max and min of this function. It's a polynomial on the following intervals. The first interval, we have x is between -5 and 12. So, all right, so this is A and this is B. Now, okay, so the first thing I'm going to do is I am going to take the derivative and set equals 0. That's how I find my critical numbers. So f prime of x, if I just use the power rule for each term in f prime of x is going to be 3x squared minus 18x minus 48. And what I'm going to do from here is I am going to set this equal to 0 because that's the goal. I want to find out what x is when the derivative is 0. Okay? And from here, what I can do is each of these guys can be divided by 3. So I can factor out a 3 before I factor this thing. And so I can factor this. Setting each factor equal to 0, I get x equals 8 and x equals -2. So these are my critical numbers, or critical points. Okay. Once I have that, I need to evaluate the original function at these. So I'm going to just kind of note this over here. I'm going to say the critical points are x equals 8, right? Yeah. And x equals -2. And I'm going to do some erasing here. So I'm going to erase all of this. And we're going to also confirm the algebra with Desmos. So I just want you guys to see how this looks graphically too. All right, so step 1, we're inputting our critical numbers into the original function, okay? Because, again, we care about the highest and lowest value of the original function, not the derivative. I remember learning this and not being clear with that, but all right, let's do it. So here we have 8 to the third. I'm going to get my calculator out because this looks like a mess already. Yeah, the calculator is going to have to do. Okay, so let's see. Okay, let's see. All right, so I'm getting negative 396. And I'm just going to hold off on this because, again, we haven't deduced anything. We're just trying to get these numbers. Okay, so I took care of that. Now let's do f of negative 2. So again, we're just plugging in negative 2 into our function for x. Okay, evaluating that. All right, so I'm getting 104 here. Okay, so we took care of the critical points part. Now we need to take care of the endpoints. So again, we're just plugging in the endpoints into the original function. And conceptually, what are we trying to do? Well, okay, so like we have this original function. I don't know what it looks like, okay? But what we're trying to do is we're trying to find these little peaks and valleys. And the peaks and valleys happen with the critical points because that's where the derivative of the function is 0, right? That's where the slope of the tangent line is 0 at these peaks and valleys. So that's the one thing we're trying to do. Then we have to look at the endpoints as well because the endpoints aren't included in the peaks and valleys, right? It could be that the endpoint is the global max or min, right? And in this case, this little stupid picture that I drew, that is true. So that's what we're doing here. All right, let's keep going. Okay, so now what I want to do is take care of the endpoints. And I'm evaluating f of negative 5. So that's just going to give me, what, negative 5 to the third minus 9 times negative 5 squared minus 48. I'm trying to write small here, but yeah. Okay, so let's see. All right, so we have negative 125, negative 225, positive 240, positive 52. Okay. Okay, so we have negative 58 is our output here. And the last thing to do is evaluate f of 12. I know this is kind of a pain, but here we are. Okay, so f of 12. Again, I'm just plugging in 12 into my function for x. All right, so I get negative 92 here. Okay, and so we have 4 numbers that came out of this. We have this guy, this guy, this guy, and this guy. And the question is, what are the global maxes and mins? Well, the global max is the biggest of these numbers. So the largest number is this guy. So we have 104. And what was the x value that corresponded to it? -2. And we're going to confirm this with Desmos, by the way. All right, so that's our answer. The smallest of the remaining 3 values is the global min. That's the smallest number, and that's going to be this guy right here. That's the smallest number. So we have a global minimum, and that is -396. And the x value that corresponded to that was x equals 8. So let's punch this into Desmos and confirm this, as true or false. Okay, so let's see. Now what I'm going to do is I'm going to put in this domain restriction, this interval right here. The way I'm going to put it in Desmos is like this, okay? And when I do this, it's going to cut the graph off and it's going to be easier to read. All right, so watch this. So I'm going to do little curly braces right here. And then what did I want? I wanted it bigger than -5 and less than or equal to 12. Okay. Okay, wait a second. Let's see. -5. Okay. I'm going to close that brace. No, I'm not. I'm going to just leave it like that. And what I should see, and what I'm not seeing, is this graph cut off. So let's see. Let's see. I might have to close out of Desmos and try this again to get the dimensions correct. And that happens sometimes. It's okay. X squared minus 48x 48x plus 52. Okay, so now I can see it. Now I'm going to put in my restriction. -5 less than or equal to x less than or equal to 12. Maybe I put in -12. Maybe that was the problem. Anywho, okay, so there it is. There's my domain restriction. And so it should show the graph kind of cut off, with the endpoints at the intervals. And so, okay, we can see from the graph that, the highest value, the highest y value is right here at -2. And that is what we got here, our global max. And the lowest should be at -396. So let's go to the lowest point on this. There it is. And that was at x equals 8. So yeah, there it is. So you can always check check Desmos to see if you did something right. All right, try this, you guys. Let's see. Yeah. All right, so try this. I'm going to do it, but I would pause the video and try it yourself first. Okay, so we need to first take the derivative to find the critical points. And we already did this because this is the same function. And I'm going to save us some work because this was the same function. This is just part B, So, all right, our critical points we already found. We're at 8 and negative 2. So I'm really not even going to do this again because we already did it. So the critical points, I'm just going to write that here. We already did this. Okay, so, and we already plugged in our x values, our critical point values, into the original function. And we got f of 8 is negative 396. And f of negative 2 was 104. Okay, so we're just going to save this. Okay, so we did critical points in the last slide. Now we need to look at the new endpoints. Well, one of these endpoints is the same. We already saw what f of negative 5 was. F of negative 5 is negative 58. So let's write that. And all we have to do is evaluate the function at f of 14 because we didn't do that yet. All right, so f of 14, 14 to the third, minus 9. Plus 52. Okay, let's see what this gives us. All right, so I'm getting 360 here. Which is our final piece of information that we needed. Now we compare the numbers and see what's biggest and what's smallest. Well, we still have the same absolute min, or global min, because that's the smallest number out of the 4 that I boxed in gold. But this time the global max is not 104 because this guy's higher. So this is the global max. And again, I encourage you to look at Desmos and check this. You know, put this into the curly braces after you put your function in and see what is the highest and the lowest value on this interval. All right. So now we have our interval is now from negative 5 to infinity. So notice that we don't have a closed interval here because infinity can't be included. It's like, you know, it's not really a number. It's just as x gets bigger, y gets bigger or smaller. So let's look at this. Now what I would do, to be honest, is I would just look at Desmos for this one because we want to see what is happening as x goes to infinity. We want to see what's happening between negative and 5 and infinity. So what I'm going to do is I'm just going to change this thing. All right. Let's see. So let's see. Negative 5 less than or equal to, right? Yeah. And then x strictly less than, and where's my infinity sign? Let's go to ABC. I know it's here somewhere, huh? I might have to like just type it out. Let's see. No. Okay. Let's type out infinity and see if that works. Infinity. Yeah, there we go. All right. So here's our function. Now, talking about the absolute minimum, we can definitely do that because there is a lowest point, and it's right here. It's negative 396 is our global minimum. So the global minimum is at negative 396 when x is equal to 8. All right, so that stays the same. So we can say for sure, yeah, this is the smallest value on the graph. But then look at what happens, okay? We can follow this thing up forever and ever and ever, right? Because, I mean, think about it. If x gets really huge in this equation, y is also simultaneously getting really huge. So we can't pinpoint a specific number that is the biggest on this graph when we talk about x going to infinity. So for that reason, there is no global maximum. All right. Let's do another example. Find the exact global max and min values for this function. Okay, so we're not really given an interval, and when that happens, you just want to assume that we're going from negative infinity to positive infinity. There's really no restriction here, what we can put in for x. Of course, you are going to have issues with the denominator, but that's neither here nor there. All right, so what are we going to do? We don't have endpoints to plug in. My thought is to find the critical numbers and see what that gives us and then confirm our suspicions with the graph. All right, so what I'm going to do, since we have a rational function, I'm going to sort of move all of this to the numerator, but I'm going to have it all be an exponent of negative 1, right? Keep in mind these two things, 1 over blah, 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 and blah, blah, blah to the minus 1. This should be a 7. Sorry. These two things are the same, all right? So now what I'm going to do, since I've made it look a little bit nicer to take the derivative of, is I'm going to use the chain rule here because I have a function x minus 7 squared plus 5 to the negative 1, okay? So if I take the derivative using the chain rule, taking the derivative of the outside, I bring that negative 1 to the front, minus 1 to give me a negative 2, and then I'm going to multiply by the derivative of the inside, okay? So I have to use the chain rule with this piece, right? Because what's the derivative of x minus 7 squared? Well, that, again, I'm taking the 2, bringing it to the front, subtracting by 1, which gives us x minus 7 to the 1, multiplied by the derivative of the inside, which is just 1. I don't really have to write that, but you get the idea. So, okay, so let's clean this up just a little bit. Whenever I'm taking derivatives and setting them equal to 0, I like to make sure that I have a denominator, especially with something complicated that looks like this, because remember, we don't care when the denominator equals 0, really. We kind of just want to see where the peaks and valleys are, and that comes when the numerator equals 0, right? The denominator equaling 0 means it's undefined. So what I'm going to do is I'm just going to rewrite this a little bit. I'm going to keep in mind that this and this are just multiplied, and so I combine these and sort of write them in the numerator just like this. So that's that. And then the denominator becomes this thing, x minus 7 squared plus 5. And since I brought it down, it's going to be to the positive 2, not to the negative 2. This is f prime of x. And now what I'm going to do is I am going to set the numerator equal to 0 to find my critical number. And I end up getting what? Negative 14 equals negative 2x. So I get x equals 7 as a critical point. So let's look for this on the graph, okay? That's, could be a possible global max or min. All right, so let's put it in. All right, let's check it out. Okay. So let's see what happens when x is equal to 7. Okay. Look how crazy this is, y'all. All right, so we can see from the graph that this is going to be the global max. That's the point we found, x equals 7. And the actual, like when I say what's the global max, I mean the y value. So the y value is 0.2. You could also find that by subbing in your value x equals 7 into our original function. You would end up getting 0.2. So that's the global max. Global min, let's see. So yeah, I don't think we have a global min because, it's saying, well, what's the very, very smallest value on this graph? Well, it looks like the very smallest value is 0, but 1 over something can never equal 0. It's going to get very close to 0 as x gets very large, but it's never going to equal 0. And so in this case, there is no global minimum. So let's say the global max is, what was it, 0.2? I think. Let's see where it was. Yeah, 0.2. And, I put that x equals 7 in there just to sort of find that point easier on my graph. All right, so the global max is at 0.2 when x equals 7. And we've established that there is no global min because we can, it's not 0 because that is not, the fraction itself is never going to be 0. It's going to get super close to 0, but we cannot claim that as a global min because it doesn't ever technically equal 0. All right, let's do this one, and then maybe I'll pause. Okay, actually, let's see. Yeah. Okay. So we want to find the global max and min of this thing on the interval 0 to pi over 2. Now I'm going to do this by hand first, and then we're going to confirm with Desmos. I don't have a problem with you guys using Desmos for your homework at all, but you should know how to find the critical numbers and stuff too. I just, want you to use it like kind of as a checking tool. All right. So let's first do the critical numbers. Now, we're given this interval, so we have an a and a b that we're going to eventually have to plug into the function. But let's find the critical numbers first by taking the derivative. Now, the derivative of x is just 1. The derivative of negative sine of 2x, well, we have to use a chain rule. So we take the derivative of the outside. The derivative of sine is just cosine, multiplied by the derivative of the inside. Well, the derivative of 2x is just 2. All right. Now, to find the critical points, we need to set this derivative we just found equal to 0. And I'm going to bring this 2 kind of in the front just so it looks nicer. I don't know. Just going to write it like that. Now I'm going to solve for x. So I'm going to first isolate my cosine of 2x by subtracting 1 from both sides. And I get this. Then I'll divide both sides by -2 to give me 1/2 equals cosine of 2x. Okay, so here comes where you have to think a little bit. Now, my interval, I'm going to just draw it out. Remember our unit circle. Pi over 2 is there. 0 is there. So really, this is A and this is B. All we care about is the stuff in this quadrant. So like I know that there are multiple places on the unit circle where cosine is 1/2. Okay, I know that it's in quadrant 1 and it's in quadrant 4, but here we only care about quadrant 1 because of that interval that we were given. So what is this mysterious angle? Well, get out the good old unit circle. So we're looking for the x value. That's 1/2, right? And that is going to be at, what is it going to be? Pi over 3, I believe. Yeah. Or if you like, 60 degrees. Whoops. 60 degrees, pi over 3. Let's just work in radians, though. Okay, so we know that this is secretly pi over 3, right? The cosine of pi over 3 is 1/2. And so we have that 2x is pi over 3. Solve for x. So x is going to give us pi over 6, right? That's going to make this equation true. X is pi over 6. So this is our critical number, our critical point, pi over 6. And so what we're going to do is we're going to evaluate the original function that we were given at x equals pi over 6. Okay, so let's do it. So we have g of pi over 6. Did I say? Yeah, this is our critical point. Pi over 6. Okay. So we have pi over 6 minus sine of 2 over 1 times pi over 6, which, oops. You can get a decimal for this. It's no big deal. Again, we're just trying to see what the biggest and smallest numbers are. Now the sine, well, this becomes 2 pi over 3 in here. Or not 2 pi over 3, sorry. Pi over 3. Now the sine of pi over 3 is the y value. So that's root 3 over 2. So this is what we have. I don't really know what this is. I'm going to have to put it in the calculator. So I'm punching in, I'm literally putting in pi divided by 6 minus the square root of 3 divided by 2. So let's see, pi over 6 minus parentheses, square root of 3 over 2, parentheses. And this is what I get. I get negative 0.342. So I'm going to just put this in my pocket. That was my only critical number. And the last thing to do is to evaluate the function at a and b. All right, so g of a is going to be g of 0. 0 minus sine 2 times 0. Now, if you put this in the calculator, if you remember the unit circle, sine of 0 is just 0. So 0 minus 0, we get 0. Put that in our pocket. The other endpoint is pi over 2. So we're doing g of pi over 2. It's going to give us pi over 2 minus sine of 2 pi over 2, right? Now this just becomes the sine of pi, and the sine of pi is 0. So pi over 2 minus 0 is pi over 2. And as a decimal, let's see what we get. Pi divided by 2 is 1.57. All right, so we have 3 numbers, 3 candidates for global max and mins. Now the global max is the highest of these, the highest number, which is this guy. So the global max is pi over 2 and it turns out x equals pi over 2. Or 1.57 if you like that. Same thing. Okay, global min's the smallest number, which is going to be this. And what did we plug in for x? We plugged in pi over 6 to get that. Okay, there it is, guys. Now let's check out Desmos. So x minus sine 2x. Let's see. All right, I'm restricting this thing, so I'm going to put my little curly braces. So we're going from 0 to pi over 2. Sorry about that. You guys hear me? Let's see. Okay, sorry about that. All right, so we are going from 0 to pi over 2. Pi divided by 2. Okay. All right. So yeah, it does look like our global minimum is at pi over 6, which we found to be the case, and our global max is right here, and that's, about pi over 2. So, okay. All right, guys, I am going to take a break. I'll see you guys in the next video for this example. Thank you for watching. Find the global max and minimum for the function on the closed interval. All right, so we have a closed interval indicated by these lines under the greater than and equal to sign. So this is our A, and this is our B, and so we know that we're going to have to plug in these numbers into G at the end to see if the endpoints are a global max or min. The first thing I'm going to do is find the critical points, and I can find the critical points by taking the derivative of this guy. So G prime of x is, so how do I take the derivative of these two functions? I have the first function is 5x, second function is e to the negative x squared over 2. Well, I have to use the product rule. And so the product rule says keep the first function times the derivative of the second function. Well, this I have to use the chain rule because I have e to the something. So I'm taking the derivative of the outside, which is just e to the x, and leaving whatever is in there, which is negative x squared over 2. So that's the derivative, and then I'm going to multiply by the derivative of negative x squared over 2. Now, this is the same thing as negative 1/2 x squared, which looks a little bit more familiar. So here we can use a power rule. Multiply by 2, and I get negative 1x in front to the first. This is so the derivative of e to the negative x squared over 2 is this whole thing in parentheses right here. That's the derivative using the chain rule. Okay, so, all right, keep the first times the derivative of the second plus, now you keep the second times the derivative of the first. Derivative of 5x is just 5. So what we want to do is maybe make this, rearrange this a little bit so that, right here, all of this stuff is being multiplied. So this is the same thing as 5x squared times, negative 5x squared because of this negative x on the inside, times e to the negative x squared over 2. All right, so just rewriting that first thing. And then, let me make this negative a little bit more clear there. Plus, I'll just write the 5 in the front, e to the negative x squared over 2. And now what I want to do is see what this guy and this guy have in common. And what do they have in common? They both have a 5. They also both have an e to the negative x squared over 2. So that is what I'm going to divide out of here. So that's what I'm going to factor out. I'm factoring out a 5e to the negative x squared over 2. And what's left? Well, with the first thing, what's left is the negative x squared. And with the second thing, what's just left is 1 when I divide this by 5e to the negative x squared over 2. And we can see if we distribute that back in, we should get what we started with. Okay, so now what I want to do is set each of these guys equal to 0 because I'm trying to find the critical points. Now, if you set this equal to 0, you end up getting e to the negative x squared over 2 equals 0, and that is nonsensical. You can't have e as a base raised to any number to give you 0, so we kind of throw this factor out. Then I have negative x squared plus 1 equals 0, and I can solve for x this way by first subtracting 1 from both sides, dividing by negative 1 next, and finally taking the square root of both sides. Now when I take the square root of both sides, I want to make sure to tack on a plus or minus. So I have two critical numbers, 1 and negative 1. So these are my critical points, and I'm going to test these in my function. So 5x e to the negative x squared over 2. So here we go. G of 1 is going to be 5 times 1 e to the negative 1 squared over 2. This is just 5 e to the negative 1/2. Whatever this is, let's get out the calculator and get a decimal. Okay. Let's see. Okay. Let's see, my calculator's giving me a weird error message. Let's see, why is this not working? Okay, I think this did work. Okay, so, all right, let's do this times 5. So this is what I'm getting, 8.24 about. Let's check on that. I don't know about this. Let's see. No, I think something's going on with my calculator. Let's try this again. All right, 5x e to the negative x over 2. Okay, so yeah, my calculator's just being weird because I'm like verifying this with the graph, right? Because, I mean, you can tell from the graph already that your global max is at 1, but the output should be 3 and some change. And the global minimum is at negative 1. But let's see. I don't know. My calculator just might be acting weird. Let's see. So I have e to the negative 1 over 2. Maybe if I put this in Desmos, it'll behave better. I'm using my graphing calculator, which is like an antique. So let's see. Let's see. E to the negative 1 over 2. Okay, that's better. Yeah, my calculator's just being weird. So yeah, we can see that this is our value here, 3.03. So let's just, for the time being, let's just put that here and do that. Now if I plug in -1 into this function, I'm doing 5 times -1 e to the -1 squared over 2. And so what I should end up getting here when I simplify is -3.03. All right. Now, if I were to plug in my endpoints into the function, well, you guys can do that. I'm going to leave that as an exercise. But you should do that. You should plug in those endpoints into the x values. Okay? You know, the -2 and the 2 after that. And then just confirm that here we have an endpoint should be at, let me see, -1.353, and the other one at x equals 2 should be at 1.353. And those numbers are, smaller than the global max and larger than the global min. And so, yeah, -3.03 is going to be the global min, and 3.03 is the global max here. Jared is coughing. The speed v of r in meters per second with which he expels air depends on the radius of his windpipe, r, given for r is bounded between 0 and 9. So this is like my A and my B. In millimeters by this function right here. Okay? What value of r maximizes the speed? Okay, so we're trying to find the maximum of this function, the global maximum. And then, we want to see what the global minimum is too. So we're going to apply the same kind of process that we've been doing by finding the critical numbers, plugging those into the original function, and then plugging in the endpoints and comparing, what is the biggest number and what's the smallest number that we get out. All right. So let's see. What do I want to do here? Well, the first thing I can do, I'm looking at this and I'm like, I don't really feel like doing the product rule for the derivative. Let's look at this function that we're given. And let's just try to clean it up as much as we can before we differentiate. So I'm noticing that I can just distribute the 0.1, right? Because everything's being multiplied here. So 0.1 is a tenth. A tenth times 9 is 9/10. And then we have a tenth times r. So just distributing that 0.1 in there. And instead of writing it as a decimal, I like fractions. So, okay. So then we have that, and we're multiplying that by r squared. So now we can distribute this guy, and we end up getting 9/10 r squared minus 1/10 r cubed. All right. Now I think would be a good time to differentiate, because we can use the power rule, and it doesn't, it's not like a weird triple product thing. I don't know. So that's what we're going to do. So I'm going to use the power rule here, and I get v prime is going to be 9/5 r minus 3/10 r squared. Okay. And from here, what I'm going to do is I'm going to set this thing equal to 0. And I'm going to factor what I can out. So what can I factor out? I can factor out an r. I'm left with 9/5 minus 3/10 r. I'm going to set each of these things equal to 0. So I get r equals 0 for my first critical number. 9/5 minus 3/10 r equals 0. Subtracting 9/5 from both sides, I get negative 3/10 r equals negative 9/5. And then I'm going to multiply by 10 over negative 3 to like cancel this out to 1, if you will. Okay, so that goes to 1. And I'm just left with r equals, well, I can clean this up a little bit before I multiply across. 9 and 3 have a common factor. So, 3 goes into itself once, and it goes into 9 3 times. 5 goes into itself once, and it goes into 10 twice. Multiplying straight across, I get negative 6 over negative 1, which is just 6. So here is another critical point. So these are my two critical points. All right. And now what I'm going to do is I'm going to plug these into my original function. And I can see that v of 0, if I plug this into my original thing, well, this is just going to clear to 0. So that's my first value here. The other one is 6. V of 6 is equal to 9/10 6 squared minus 1/10 6 cubed. Okay. And then I'll simplify this. So 9/10 times 36 for 1 minus 1/10 times, let's see what this is. This is 216. I'm just going to punch this in the calculator and see what we get. Okay, I'm getting 10.8 here. All right, the last thing to do is to plug the endpoints in to make sure those aren't the global max and mins. So the endpoints were 0 and 9. We already did 0, so let's try 9. So we get 0 here. All right. So the smallest value here is 0. That occurs at x equals 0 and x equals 9. So that's our global min. So our global min is 0. And our global max is this 10.8, our largest number out of the bunch. All right, so here comes optimization and modeling. So for these problems, you're going to have to draw a picture. I think that's step 1. So let's write it out. So step 1, draw a picture and label as much as you can. And label. Okay. All right. So let's read what we have. And it says a farmer has 2,400 feet of fencing, and he wants to fence off a rectangular field that borders a river. Okay. So let's draw that as a picture. So here's the river. And he has fencing, and he's going to fence everything but not the riverside. So rectangular. So here's the So here's the field. It's all grassy. And then maybe the river is right here. I know it says straight river, but whatever. All right, so that's our picture. And he has 2,400 feet of fence. Okay, so what does that tell me? Well, that tells me that, he has enough, he has 2,400 feet of fence to basically put along the perimeter here. So for these problems, honestly, just start writing whatever you know, and hopefully everything will fall into place. It's kind of a dumb strategy, but it works out for me. And once you practice these problems, you'll get much better and better at them. But all right, so the first sentence is done. We don't have any more information to add here. We have 2,400 feet of fencing, and he wants to fence off a rectangular field that borders a river. And that's it. There's nothing else we can add to this picture. The second sentence says he needs no fence along the river. So that's really, not anything we need here. It says, so here comes the question. So what are the dimensions of the field that has the largest area? Okay. So we want to know what the width of this field is and what the length is so that the area is maximized. So step 2, write a formula for what you are trying to either maximize, let's see how much time we have. Okay. Either maximize or minimize. So we need to figure that out. What are we trying to maximize? We're trying to maximize area. So we need to write a formula for that. Now the area of a rectangle is just width times length, length times width, if you like. So here's our formula that we're trying to maximize. Okay, here comes step 3. So step 3 is use the info in the problem to replace a variable in the equation you are working with. So the equation we're working with is A equals XY. What step 3 is saying is you want this thing in one variable. Right now we have 2, which is not great. So we need to use the fact that we know that the perimeter here has to equal 2,400 feet. We have to use that fact to make a substitution. So helpful hint, if you're ever dealing with perimeter, or if you're trying to maximize perimeter or area, chances are that you're going to have, if you're trying to maximize area, you're going to have a perimeter formula. If you're trying to maximize perimeter, you'll probably have an area formula. Not all the time, but that's a good place to start. So we definitely know what the perimeter has to be, and we can write an equation to represent that in terms of X and Y. So this is what step 3 is about. Now, the perimeter is all the sides added up, which is just X plus Y plus X. So the perimeter is just, and by the way, the perimeter is 2,400, so I'm just going to put that there. The perimeter is X plus Y, right? Because again, we're not fencing off the side of the river. So this is just 2x plus y equals 2400. And what I want to do is I want to get a variable alone so that I can sub it in my equation that I really care about. I want this in one variable. So I am going to isolate y. You could isolate x if you want to, but I think it's easier here to get y by itself. So that's what I'm going to do. I'm going to subtract 2x from both sides to get that y is the same thing as 2400 minus 2x. Key substitution that we're going to do right here. All right, so that's the goal. The goal is to get the thing that you're trying to maximize or minimize in one variable. Once you do that, it's a breeze. Let's do it. All right. So this is what I'm trying to maximize. And again, we can cheat if we wanted to. We could look at Desmos and look at the global max. But let's do this the old-fashioned way first and find our good old critical numbers. So the critical numbers, we need to take the derivative. And I get 2400 minus 4x from using the product rule. The power rule. To get the critical numbers, we set that equal to 0, and of course solve for x. We should get 1x, and that is, let's see. We get 600. Okay. So let's double check that this is indeed true, that 600 is going to be the x value that maximizes the area of this field. Let's check it with Desmos. Okay, so this is our area function. Let's put it in. 2400x minus 2x squared. And I might have to close out of this. We'll see. No, maybe not. Okay. Right. All right. Let's see. Okay. So yeah, I gotta maybe mess with the window a little bit, but you know, it's a parabola. Here's the top, and yeah, it happens at x equals 600, y equals 720,000. And you could have found that by just, plugging in x into one of these equations that we came up with, and solving for y. So let's go back and say, okay, what are the dimensions? So we found x and y. So those are the dimensions that is going to give the largest area with this constraint that we only have 2,400 feet of fencing. So yeah, these problems are kind of crazy. I think they're fun because you have to draw a picture and kind of think about it. But like I said, you can always sort of, like, once you draw the picture, you can kind of like confirm your work with Desmos. And yeah. So what I would do, okay, when I go to the next problem, I would pause the video and see if you get the picture right, because that's the hardest part, to be honest. All right, guys, here is our next optimization problem. See if you can draw a picture and set up some equations, because that is the hardest part here. So let's get going. Now, the first sentence says 1,200 centimeters of material is available to make a box with a square base and an open top. Find the largest possible volume of the box. So we know for sure from the last sentence that we are maximizing a volume equation. So that's what we know from the last part of this little blurb. The first part, so let's just go ahead and draw a box. And it might not look like it has a square base, but let's assume that it does. Let's assume that the base is square. And so this is going to be the top of my box right here. It's an open box. And we're told that we have 1,200 centimeters squared of material. So that's telling me that the area of this cardboard or whatever material it is going to add up to 1,200 centimeters squared. So the surface area of this equals 1,200 centimeters squared. Surface area just means I take the area of each of these pieces. There's 6, squares that make up this, but we're not going to count the top. So actually there's 5, right? And so we just take the area of each of those pieces and add them up. So let's come up with an equation for that. The surface area equaling 1,200. Well, I know, what pieces is this box made out of? We have the sides. We have the bottom. We're omitting the top. And then we have the front and the back. So we have 5 sides to take the area of. Now, I know that since the base is square, all of these guys we can just call X, these little sides of that bottom. And, we don't really know what the height is, but we can just call it H. All right, so here's side 1. So the area of side 1, and, look, it's kind of hard to describe this, but this is what I'm calling side 1, and this is what I'm calling side 2. Okay, so side 1, the area of this, well, the area of a rectangle is just base times height, or length times width if you like, so it's just XH. And side 2, it's going to be the same thing. We just have, the height and the base. All right, so it covers my sides. Now the bottom is going to, base times height is just X times X, which is X squared. So that's the area of the bottom. And then the front and the back is going to have the same area as side 1 and side 2, because I'm doing the front in red. If you can see this. The front and the back are both going to have a base of X and a height of H. So we just add up these areas and set it equal to 1,200, and we have a nice little equation. Let's do it. All right, so we have XH plus XH plus X squared plus XH plus XH, that's all of my faces, equals 1,200. And I can combine like terms. These guys are like terms. And so how many of those do I have? 1, 2, 3, 4. I have 4XH plus X squared equals 1,200. And so let's just leave that alone for now. Let's just put it in our pocket right here. What are we trying to maximize is the volume. So let's go ahead and write that. That's very important. So the volume, basically to find the volume, you just take the area of the base times the height of a figure. So the area of the base in this case is X squared times the height, it's just H. And remember, our next step is to get this all in one variable. I like the variable X personally. And we need to we need to use our other equation that we found down here to figure out what h is in terms of x. So let's do that. Okay, so I'm going to isolate. Should I isolate h? I don't know. That might actually be more work. Yeah, I don't know. Let's just isolate h. We'll see. It doesn't matter either way. So if we subtract x squared from both sides, again, I'm trying to get h in terms of x so that I can sub it in right here. That's what I'm trying to do here with this other random equation that I have. And I'm going to go ahead and divide both sides by 4x to get h alone. And I'll just sub it in now. I have x squared times h, which is this mess. 1200 minus x squared over 4x. And let's clean it up just a little bit before we start taking derivatives. Now, since this is understood to be over 1, I can cross divide out an x. And once I do that, I can distribute the x in there. Make this look a little bit better. So I get v equals 1200x minus x to the 3 over 4. And since I know I'm going to take the derivative, I can write this separately, without the whole denominator of 4, so I can do the power rule. So 1200 divided by 4, that's going to be 300x minus x to the 3 over 4 is just this, right? Same thing. Now I can go ahead and take the derivative, because what am I trying to do? I'm trying to maximize this, and so I need to figure out where the derivative is equal to 0. Okay, so if I take the derivative, I get 300 minus 3/4 x squared, and then if I set this equal to 0, I get 300 minus 3/4 x squared. Subtract 300 from both sides. And then I'm going to multiply both sides by 4 over negative 3. So that these, cancel out. All right, what is this going to be? This is going to be 400 equals x squared, I believe. Yeah. Then I need to take the square root of both sides. And since I'm dealing with lengths, widths, and stuff, it doesn't really make sense for me to tack on a negative here, so I'm just going to use a positive version. So x is equal to 20. All right. Now, what was it asking me? It was saying, what's the largest possible volume? So we need to figure out what h is first, because I need two things to plug in here. I need x, which I have, and I need h. And so I can go ahead and, use one of these variations of formulas that I found right here, plug in x into that sucker, and get h. All right, let's see what we get here. What am I getting? I'm getting 10. So that's that. What's the volume? The volume is x squared times h. Plug it in. Plug in your stuff. And we should get 4,000. So the maximum here should be, and by the way, what are my units? Well, volume is always in units cubed. So here my units are going to be centimeters cubed. That's my maximum here. And again, we can go back to Desmos, plug in this thing, and see if we're right. So let's do it. My window's messed up. I might have to actually, let's exit out of this and go back. Okay, let's see. Oh, yeah, I just needed to zoom out a little bit. All right, so let's see. Where is my maximum? Now, this is kind of an important an idea here. Now, you might say, well, Sarah, that's not the highest point on the graph. We can go up and up and up, and it's higher and higher and higher. But think about this, okay? We're talking about a real world situation here where our x value is a dimension of a box. And you can see that that's getting higher and higher. Well, look at what x is. X is negative. That doesn't make any sense. So x has to be bigger than or equal to 0 for this problem to even make sense. And so, yeah, this has to be our maximum right here. The volume being 4,000 for x is equal to 20. All right, there's a problem kind of similar to this on your homework. Find the point on the curve y equals square root of x as closest to the point 2, 0. All right, so we need to draw a picture of what's happening. What kind of information are we given? Well, we have this function, y equals square root of x. That's for sure. So let's kind of sketch that. I'm just grasping at straws here. What do we have? So, yeah, all right. So we have this, maybe it looks something like this. I don't know. Square root function. This is the square root of x. And we're interested in knowing which point on this curve is closest to this guy, which is 2, 0. We're trying to figure out, oops, let's do this. So what point is this? Now think about it. Are we trying to maximize something or minimize something? Well, we're trying to minimize the distance between the curve and the point 2, 0. So let's write that. We are trying to minimize distance. So we have to come up with a formula for distance. Now, you can just Google this if you want, but the distance formula is this. The distance formula between 2 points on the plane is, basically Pythagorean theorem. X2 minus x1 squared plus y2 minus y1 squared. So we're trying to minimize this function, but we need to plug stuff in because there's too many variables. Like, what is happening here? The idea here is to just get something in terms of x so we can differentiate and call it a day. So the question is, what do we put in for x1, x2, y1, y2? Think about it for a second. Think about it. So this formula, this distance formula, is telling us the distance between 2 points, x1, y1, and x2, y2. So in our case, definitely x1, y1 we have. This is one of the points. And the other point, we need to get creative and name it. That's this point, which we don't really know what it is. We don't know numbers for it yet. But what we do know is that it has an x value. And at that x value, the y value is square root of x. Really, that's all we can say. So this is our second point, x2, y2. All right, so let's think about it. Does that make sense? Yeah, okay. Right. So let's go ahead and sub everything into our distance formula. And we get, so let's do the square root of x2. So we have x minus 2 squared plus square root of x minus 0 squared. And we're already in a great position because, look, we only have one variable x. Let's clean it up a little bit. So I know that I'm about to differentiate this thing because it's the thing I'm trying to minimize. And we don't like square roots, right? When we differentiate, we like powers. So what I'm going to do is, instead of writing this under a radical, I'm going to say this is x minus 2 squared. Now, the square root of x minus 0 squared is just simply x, right? Square root of x squared is just x. Okay, so yeah. And I'm going to write this to the 1/2 power instead of that ugly square root. All right. Now, I need to take the derivative. And I need to use the chain rule, right? So what do? I take the derivative of the outside first. So 1/2 times x minus 2 squared plus x. Now if I subtract 1 from 1/2, that's going to give me a negative 1/2. And now I need to multiply, and of course I'm going to run out of room here, but maybe I'll just do like, I don't like that. Times, I'm going to write it down here. The derivative of the inside, which is all of this. Well, the derivative of x is just 1. The derivative of this, I need to use the chain. And that's pretty much it. All right, so let's clean this up. Again, this is just cleaning stuff up. Right, okay, so 1/2 times x minus 2 squared plus x to the negative 1/2 times, in orange, 1 plus 2x minus 4 if I like FOIL that out, or distribute it rather. And then I can, whatever, worry about this later. Okay, so there's the derivative. Now I need to set the derivative equal to 0. I have this ugly, ugly, ugly expression. But what I can do to make it look prettier is to say, okay, well, the negative 1/2 business, whatever is being raised to the negative 1/2, I can bring to a denominator. So, and that's going to help us because then we're just going to set the numerator equal to 0 and it's going to be fine. So what I have is, well, this is part of the numerator right here. Okay, this is part of the numerator. Multiplying those together, I just get, and I know I'm not combining like terms yet. Don't know why, but whatever. Then we have 2 in the denominator, and now this big piece is going to the denominator because I don't like it. I don't like working with things like this. And when we move it to the denominator, that exponent becomes positive. All right, so now all I have to do from this point is set the numerator equal to 0. All right, so I have 0 equals 1 plus 2x minus 4. So 2x minus 3 equals 0. All right, so the x value is going to be 3 over 2. Now, what is the y value? Well, the y value I have to just plug into my original function, because we're trying to figure out what that point is. And so I need to plug in root 3 over 2 in here into the square root of x. So y is equal to the square root of 3 over 2, which is just a weird number, but this is how you do it. So that is the point that is closest to 2, 0. The top and bottom margins of a poster are each 6 centimeters and the side margins are each 4 centimeters. If the area of printed material on the poster is fixed at 384 centimeters squared, find the dimension of the poster with the smallest area. So let's go ahead and draw our picture. So we have some kind of poster. And we have, there's margins on the sides and on top. So it's, something kind of like this. And we know that the printed area is going to be 384 centimeters squared. So it's going to be this portion right here. We're told that the top and bottom margins are 6 centimeters. So that means this guy is going to be 6 centimeters. This guy is 6 centimeters. This guy is 6. And we're told that the side margins are 4 centimeters. And so what are we trying to do? We're trying to find the dimensions of the poster with the smallest area, okay? So we are minimizing. We are trying to minimize area. And what area are we talking about? Well, we're talking about the whole thing. We're talking about the 384 plus the frame around it. That's what we're trying to minimize. So the first thing I'm going to do is I'm going to kind of, we're not told a whole lot about the, the blue region, the area. We don't really know what the dimensions there are. But what I'm going to do is I'm going to say, well, this blue area has a width of x. And I'm going to say that it has a length, or a height if you like that better. I'm going to say that the height's y of this blue area. And so now I have a formula for the area of that blue region. I say x times y equals 384. And now what I'm going to try to do is I want to get the area of the entire thing in terms of x and y, right? I don't want to start introducing new variables because it's going to get super confusing. I want to just keep it in terms of x and y. So how can I write, first of all, how can I write the length right here of the, the thing that we're trying to minimize? How can we write this length in terms of x? Well, I know that, x is made up of it, right? This part here is x. That's the length there. But it's also made up of these little margins right here. And that's going to be 4 and 4 because of those. So what I can say is that, this long piece is secretly x plus 8. Okay? So I'm going to erase that. I'm going to erase that. And I'm going to say this whole thing right here. Let's see. This is x plus 8. And maybe I'll do it in a different color. How about gold? I'll do it in gold. So that's one of the dimensions we're trying to minimize here. So if that's x plus 8, this is x plus 8, just so we have that. And how can I write the height, or the length, if you will, in terms of y? Well, again, we kind of do the same trick here. We know that this piece right here is y, that height. And then we have these corners to add, and those corners are 6 centimeters. So this is going to be y plus 12. So each of those guys are going to be y plus 12. All right. So now we're in a good position because we can explicitly write the area we're trying to minimize in terms of x and y. And we can use this other formula to do a substitution. Okay, so the area we're trying to minimize, I'll do in black. We are trying to minimize the area x plus 8 times y plus 12. All right. And let's see. What I'm going to do first, I'm, going to leave this and not really distribute first. Remember, when you're trying to minimize or maximize, we want to take the derivative. So I want this a equals x plus 8 times y plus 12 to only be in terms of x or only in terms of y. So what I'm going to do is I am going to get y in terms of x with this equation right here. Y is equal to 384 divided by x. So that's the piece of information I need to do the substitution right here. So let's go ahead and do that. I have a equals x plus 8 times 384 over x plus 12. All right. Now what I'm going to do is I'm just going to FOIL this thing out. First, I get 384 because those x's are going to cross cancel. Outer, I get plus 12x. Inner, I might need a calculator here. Let's see, 384 times 8. 384 times 8, I got plus 3072 over x. That's my inner. And finally, my last is going to be 96. Okay. I'll write it down here again. And actually, since I'm taking the derivative, I'm going to write this like this. X to the negative 1. So I can use the power rule pretty easily. All right, now I need to take the derivative. And remember, constant numbers go away when I take the derivative. And so I'm just left with 12 minus 3072 x to the negative 2. That's it. That's the derivative. So what I can do from here is to find the max or min. Remember, I set the derivative equal to 0 to find those peaks and valleys. And I'm going to put this x squared under there to make it a little bit easier to work with. All right. So what I want to do, I'll first multiply both sides by x squared. Now, I know that I can do that because x is a dimension. It can't be negative or 0. So there's really no problem doing that. And when I distribute this guy, I end up getting 0 equals 12x squared. Oops. Minus 3072. I can add 3072 to both sides to get me this guy. Let's see what this is divided by 12. I get 256. Take the square root of both sides. And of course, I'm just going to take the positive answer here since we're dealing with a dimension. Okay, so I get x equals 16. All right, so what was the original question asking? What are the dimensions of the poster? Well, the dimension wasn't x, right? That was the dimension of the smaller area inside the poster. The dimension is x plus 8. So that's going to be 16 plus 8 is 24. So this is one dimension, my answer. Well, actually, let's just do it like this. So 1 is 24. The other dimension is y plus 12. Well, we have this equation over here, this convenient equation relating x and y. So if I plug in my x, which was 16, 384 divided by 16 is going to give me 24 for y. So I have 24 plus 12 is my other side. And that's going to give me 36. So my final answer here, is one side, it's 24 by 36. That's my answer. All right. Okay. A new soda can is going to be made to hold 16 fluid ounces. Find the dimensions that will minimize the amount of material used in construction, assuming that the thickness is uniform. Note that 16 fluid ounces equals 28.875 inches cubed. Okay. So the first thing is, what kind of shape are we dealing with a soda can? I mean, you don't really usually drink soda out of like a box shape. So I think the closest shape to a soda can is probably like a cylinder kind of shape. Or at least, a shape that we can easily take the volume and surface area of. So here's our soda can. And we are given something, the 16 fluid ounces. What is that? Well, that's the volume that the can can hold. All right. So we're given the volume. The volume is 16 fluid ounces. But since I'm gonna look for, the dimensions and stuff, I'm gonna actually use this piece of information that says that the volume here is actually 28.875 inches cubed. Because, 16 fluid ounces, that's not going to really give us anything in terms of inches and stuff. So, yeah, I think this is more useful. So that's the volume. We're given that. And there's kind of two components to a cylinder that you need to have to take the area and the volume. You need the radius, it's like the distance from the middle of the can to outside, and you need how tall the can is, the height. You need those two things. And the volume of a cylinder, basically the volume of any kind of 3D shape is the area of the base times the height of it. Now the base is a circle, and the area of a circle is pi r squared always. So the base times the height, area of the base times the height is our volume. And so now we have this equation. We have 28.875 is equal to pi r squared times the height. So we'll just kind of keep that in our pocket. And we're trying to minimize the amount of material used. So the surface area, right? So how do we find the surface area of a cylinder? Basically, we're just trying to find the area of both of these circles, top and bottom, and the area of this wrapped up rectangle, and add them together. And there's if you don't like this idea of dissecting it and adding them up, you can look at the formula on Google. But this is the way I do it. So the surface area of a cylinder. So the surface area, this is what we're trying to minimize. So let's get an equation here. Well, I know that the first two parts are the top and bottom circles that I need to find the area of. And I already said the area of a circle is pi r squared, so two of those areas are going to be 2 pi r squared. So that's the circles. Now we need to think about the area of this rectangle that's wrapped up into a cylinder. Like, you can imagine you have this rectangle, and like you wrap it up basically to a tube to make a cylinder, and you have like the height of the rectangle, which is our h here, like that's our h. And then what's the width of the rectangle? Well, imagine this thing, wrapping around. That's going to be the circumference or the perimeter of this circle. That's the width of the rectangle. So what's the circumference of a circle? 2 pi times the radius. Okay? And therefore, the area of this rectangle is just length times width, and that's it. That's the formula. Great. All right. Now we have too many variables in the surface area thing, right? We want to only be in one variable. So the question is, what should we replace? I always want to replace the variable that has the fewest occurrences, I guess, which is h in this case. So I need to use this thing that I put in my pocket to get h in terms of r so that I can do a substitution. Well, here, all I have to do to get h by itself is divide both sides by pi r squared. And there it is. So that's h. So that's what I'm going to substitute here. Now, I'm going to clean this up before I take the derivative with respect to r, because this is a mess, really. I mean, too many pi's, too many r's. I don't like it. So let's go ahead and simplify this as much as we can before we start to differentiate. Well, I'm multiplying here, and so what I notice is that I can cross-cancel these pi's, and I can cross-cancel an r on top. And then we're left with one r on bottom. All right, so let's clean this up. Let's see, I don't like fractions, so that's what happened here. Now, 2 times 28.875, let's see what that is. 57.75. And then there's r on the bottom. I know I'm going to have to differentiate this thing, so I'm just going to move it to the top and give it a -1 exponent. All right, great. Now I have to take the derivative, because that's what I'm trying to minimize. I need to take the derivative and set equal to 0. So remember, guys, 2 pi, even though it's weird looking, it's still a number. And so, we just act like this is like a 2 or a 3 or a 4. We just apply the same kind of power rule to it. So the power rule says multiply the front. So you get 4 pi and take 1 away from the exponent. Same thing here. I get -57.75 r to the -2. Okay, now what I want to do is set this equal to 0 and solve for r. And again, I go back and forth with the r squared on the bottom or the r to the -2 on top. It just depends what you're trying to do. They mean the same thing, but here, I really like getting rid of denominators, so that's why I put that there. And I know r can't be negative or 0 because it's a radius distance. So, to get rid of that r squared on the bottom, I'm going to multiply both sides by r squared to clear that out, and I have to distribute that thing in there. And so what I get is 0 equals 4r cubed minus 57.75. I'll solve for r. Add 57.75 to both sides. Equals 4r cubed. And now I'm going to divide by 4. So let's see, 57 divided by 4. I'm just going to 14.4375. Okay, now I have to take the cubed root of both sides. Another option, if your calculator doesn't have this feature, is you can raise both sides to the 1/3 power to cancel out that exponent of 3. And I'm gonna have to, let's see, maybe I should do this. I'm actually gonna check this on my desktop on Desmos. Give me one moment. Okay, let's see. 14.4375 to the 1 divided by 3. Okay, I'm getting r is equal to about 2.43. And what were our units? Inches? Alright, so what did they want? I have to go back and see what they wanted. Find the dimensions. Okay, so we have r. We found r. And we need to find h. And we have this very convenient formula to find h right here. H is equal to 28.875 divided by pi. R was 2.43 squared. And let's punch this in the calculator. Let's see what this gives us. Okay, so I'm getting h is about 1.56, and our units are inches. See, that's why I use that little conversion thing, because I was looking for dimensions, and I knew that if the volume was in inches cubed, then the radius and the height would be in inches. All right, so there's our height, there's our radius, ba-bam. Okay, next. Engineers are designing a box-shaped aquarium with a square bottom and an open top. The aquarium must hold this amount of water, so that's a volume. Let's put that in our pocket. What dimensions should they use to create an acceptable aquarium with the least amount of glass? So again, this is asking for, this is an area problem. It's asking for, we want to minimize surface areas with that saying, the least amount of glass. Minimize surface area. All right. So let's, this is where our picture comes in. We have our fish tank or whatever is going to be in this tank. I don't know. There it is. And we have this open top. So when I do this area calculation, I'm not including this upper face of the rectangle. Now it tells me that the base is square. So that means all of these sides on the bottom are equal. I'm going to call them X. So all four at that bottom are equal. Now, we don't really know what the height is, but I'm going to call it h. Now, let's use the volume formula for a box. So remember, volume is just the area of the base times the height. Well, the area of the base in this case, let's rewrite this. The area of the base in this case is x squared, right? Base times height, times the height. So that's We're going to just put this in our pocket for a second. Keep that in mind. And now we need to come up with our surface area formula because that's what we're trying to minimize. Right. Okay, so we have, and we can break it up again. Now, we don't have a top, but we do need the area of the bottom. We need the sides. We need side 1, side 2, and then we need the back and the front. We need all of these areas. Then we're going to just add them up. And again, there's a formula or something on Google, but this is how I do it. This makes sense to me. So here we go. The area of the bottom we just discussed was x squared. The area of the side, well, let's look at this. Let's look at the sides. Here's the side. We have base x times height. All right, so x times h. Again, side 2, since they're, facing each other, they have the same base and height. The back and front are also going to have an area of xh. X times h. So here's my front, and you can see that it has a base of 5 and a height of h. All right, so the total area, what we're trying to minimize, is just equal to, how many of these do we have? 1, 2, 3, 4. So we have 4xh plus we have an x squared. And now I'm looking and I'm seeing I got to make a sub here. I'm going to sub in, h. This thing that I put in my pocket, let's solve for h. So, let me erase some stuff. Remember, I just want to be in one variable before I differentiate. So in this case, when I divide both sides by x squared, I get that h is equal to 1372 over x squared. And I'm being sloppy with my units, but that's okay. So let's put it in. So our surface area is now in one variable. We are in a very good position to differentiate. And, all right, so let me go ahead and differentiate this. Well, let's simplify it first. 1x can cancel out here with 1 down here. And I can multiply the 4 and the 1372. That's pretty much all I can do. Okay, so let's see. 4 times 1372. And then I'll write x to the 1. No, x to the negative 1. Sorry, guys. All right, let's differentiate this sucker. So the derivative is just negative 5488 x to the negative 2 plus 2x. Set that thing equal to 0 and solve for x. And I'm going to start by getting rid of the denominator. That's just the easiest thing I see to do. And I'm going to multiply both sides by x squared. So I get 0 equals negative 5488 plus 2x cubed. Solve for x cubed. And I'm going to kind of do this. Let's see. So this is 2744. And again, I want to take the cubed root, or I want to raise both sides to the 1/3 power. So I'm going to do that in Desmos. And I get 14. Okay, so what dimensions? Well, yeah, so we have x is 14, and to find height, we're just plugging it in here. Over 14 squared. And we get 7. So my final answer is that x equals 14, h equals 7. Alright guys, I hope this video was informative and helpful, and thanks for watching. See you guys next time.